16, 14. Okay. Let's get started. So, any question from this time? If not, so this time we started going into this new chapter of classical computer science. As you might see, this chapter has much less computation. This is mostly teaching about some basic knowledge in computer science. So to get everyone familiar with the ideas of computer science and some notations. So we start with the most basic concept of computer science. That's this Turing machine. This is a very fundamental definition of what is a computer. Very abstract definition. So we think a computer is composed of this Turing machine that has an infinitely long tape and some rewrite head, and then there is this CPU part where you have programs stored. What? Excuse me. Where you have some programs stored inside your, also hard coded in your CPU, and there is finite state control. This is like a memory, and this tape can be seen as your hard disk. So the input will be written on the tape at the start of the computation, and the read-write head will start at the starting position, and the machine will move the head and read-write on the tape according to what the program says, and at the end, whatever left on the tape is the output of your Turing machine. And now a very basic question of studying the Turing machine is that we just say at the end, whatever on the tape is your output. But what is the end? So the end is when the program halts, when the machine halts. But the machine might not halt. As you know, there are some programs that just give you infinite loop. So maybe your program is just your head keep moving left and do nothing. Then your program will never halt. Okay. So, yeah, the very basic question about a Turing machine you can ask is, does it halt or not? And this brings us to the, I guess, the world's first complexity theory study on computer science. This is a complexity theory when people don't have computers. So we don't have back then we don't have the concept of P versus NP, because we think whatever can be computed by a computer, then the machine will run very fast and it will just be done very fast. So people want to study where things are actually computable or not. And we find out that this halting problem, this very basic problem of halting problem, is actually not computable, or more precisely, is in the class of being undecidable. And that means that there's no Turing machine that can decide whether other Turing machine will hold or not. And let's go into the more detailed definition. So, one thing about the Turing machine that we didn't cover in the previous review is that we can count the Turing machines, okay? Because the Turing machine is basically specified by the size of its memory and the program lines. And those are all returning some discrete numbers, so it's very easy to count those. There are infinite number of possible programs, but you can count them. So you can assign a number to each different machine, and that number we call Turing number. And so that's just a easy way to count Turing machine. And now our halting problem. So the most general halting problem you probably want to see is, does the Turing machine number x, so you just use this number to, as we said, this Turing number to label a Turing machine. So does this Turing machine x hold on some input y? Obviously, a machine holder will not depend on what the input you feed on it. Okay. So this problem has two inputs, x and y. And we want to determine that it's holder or not. So your problem answer should be yes if this holds, or no. That means this Turing machine x will, when you feed it input y, it will loop forever. Yeah. And this problem we are going to show is undecidable. So before we go into start doing actually proof, any question about this quick review of Turing machine and the definition of the problem? Okay, no. Okay, so let's start our proofs. So we start with little reduction. So this problem is hard, but it's a little annoying. We make an easier problem. So we make a problem prime. That is, does the Turing machine number x hold on input x? So we put this this Turing number on a tape and feed it into the machine itself. So basically, we're asking, does the machine hold on itself? Yeah, Turing number is just an integer. It's a countable number, so we think it as an integer. And we can write the integer in binary, so those are 0, 1s on this tape. Okay. And well, there are some details, like you will keep the starting symbol here, but those are okay. Yeah. So this Turing number is an integer. This is easier. Mm-hmm. And so now we consider this problem prime is still very hard. We are going to show the problem prime is undecidable. And now we introduce a little more notation to make it a little easier. So we assume this problem prime is solvable. So if it is solvable, then we can define its answer as some function. So we define this halting number h of x as whether this problem prime solved as yes or no. So yes is output as 1. That means so h of x equal to 1 if the answer to this question is yes, it holds. So that means the Turing machine number x will hold on input x. Then we say h of x equal to 1. And otherwise, if the Turing machine x does not hold on input x, then we say this h of x equal to 0. Okay, so this is just a notation to say whether the answer to this problem prime is 0 or 1 when you put x into it. Okay. And now this is a formal statement of our undecidable theorem. So no Turing machine can compute h of x for all x. So there is no Turing machine. Remember, Turing machine looks like this thing. So there is no Turing machine where you put h of x here, and you will look up the there's no Turing machine where you put write x here, and it will do some computation, and in the end write h of x say the first bit. That's not possible. And why is that? Because we can do by contradiction. So we suppose there is a Turing machine hot that do this thing. Then the idea is we'll kind of do a feedback loop to let hot run on itself, but we do a inversion, do some reverse. Then we create some logical contradiction. Okay, so that's a high-level idea. And the detail is that, so we suppose there is a machine hot. Okay. So this hot will compute h of x, and it should also hold, right? Because for all x, you need to compute this thing and stop to output. And we assume this exists, then we construct a very contradictory machine that we just called Turing. Yeah. So there are two machines. Hot should compute h of x, and there is this Turing that is basically hot, but you flip it around like this. And yeah, so we didn't exactly describe this as a Turing machine because it's very unwieldy. So we describe this in this pseudocode. So our Turing, well, you will take some input x. That's probably some Turing number. We think this as a Turing number because it's like hot. And well, first it will compute this variable y. That is, it will call hot of x. Okay? And this is possible because we assume hot exists. So you will first see whether x will hold on itself. So you call this hot to compute the h of x. And then you do this very contradictive flip around. So if y equal to 0, then this Turing x will just hold. And but otherwise, if y equal to 1, then this Turing x will loop forever. Okay? So it's very simple. It basically do hold and depend on whether hold is 0 and 1, and it do the reverse thing. Okay? So why does this create a contradiction? Is now we consider what happens if we put this Turing back into hold, basically. So that is, we consider what's the hold of Turing. Does the Turing hold on itself? Okay. So this hold is yeah. So h of t is basically does the Turing machine this this Turing algorithm we define hold on itself. Okay. Obviously, it has a Turing number t here. So we consider h of t. Okay. And then we prove that h of t can neither be 0 or 1. Because we can do some logical traceback. So if h of t equal to 1, then by definition of this h, it means Turing of t holds. Right? Because remember back here, h of t, so it equal to 1, that means the machine will hold on itself. Okay? So Turing of t will hold. Then then we look back here. So we think about how Turing of t will do. So Turing of t will, well, it will hold, then it must end from here, right? And then that means y equal to 0. But if y equal to 0, then that means hold of t also equal to 0, because y is hold of the input, hold of t. But we just say h of t equal to 1. Then we prove it, then we conclude that h of t must equal to 0. So that's a contradiction. And what about the other way? The other way is very similar. So if h of t equal to 0, then that must means Turing of t will loop forever. And if you look up Turing of t, then the only way it end up looping forever is stuck here. But if it's stuck in here, then it means it must first compute that y equal to 1. And that means hold of t equal to 1 and h of t equal to 1. So that's also a contradiction. So we find out that this h of t and the Turing of t gives you a contradicting self-loop. And anyway, so however you compute it, it gives you some contradiction. So h of t cannot be any value because it's either 0 or 1, but it's not 0 and it's not 1. And the only conclusion we can have is that this hold of x exists is actually not possible. So there is no Turing machine, or more generally no algorithm that compute where our algorithm hold for all algorithms. Okay. So any question on this holding problem? Yeah. So this is I guess biggest separation in complexity theory. That is, some problems are simply not computable. But in practice, as you might feel, most problems we encounter are decidable. Just is something that you can need to keep at the back of your mind. That sometimes there are this kind of problem. Okay. Now we are pretty fast. Okay. So that's Turing machine and the holding problem. They are very fundamental of complexity theory. Then we go to more practical formulation of computer science. That is the circuit model. And this is also how we are going to think about in quantum computation. So circuit model are composed of wire and gates. Okay. So we think, so now this is very physical. We think about our information flows through some wires, so maybe it's just some electrical wires. And those wires will send 0 or 1, will carry a 0 or 1 through them. And there are gates that will do some computation on the wires. So it will accept the input from the wire, so say it's 0, 0 here, and it will depend on the input, do some deterministic computation and give an output. Then the output can be fed into another gate and then we will get more. So this output from this gate will become input of this gate, and this gate see this input of 0 and 1 and it will do some more output. So maybe a gate can have more output than input, etc. And maybe there is another gate. And at the end, you can look up whatever left over on your wires as your output. Okay, so that's circuit model. Is I think it's more practical than Turing machine. But if we compute the Turing machine, you will see the circuit model is a lot less general because when you write the algorithm in circuit model, obviously an algorithm you can write in circuit model. You can say you place some gate here, some gate there, and you will do some computation. But first thing you notice is that if you write in circuit model, then one of these picture has the fixed number, fixed input size, right? So for example, this picture here, the input you have 3 lines, so you have 3-bit input. And that's different from Turing machine. Turing machine, you can have arbitrary input size. This tape is infinitely long. So the algorithm for all input size is just described by one Turing machine. But for circuit model, one circuit is one input size. So we'll talk about the discrepancy of this later. But for now, this is circuit model. You can have a circuit, it will do some computation. It represents some function. You can have the input of your function and the starting of your wire here. And you will have an output of your function here. And some notation thing is that throughout this class, we think the time flow from left to right. So we think the left side of our circuit is the input, and and time just flow this way from left to right. And so whatever left side of the gate is the input and the right side of the gate is the output. Okay. And this is a bit confusing because we'll see later in quantum computation, if you think about multiplying a whole bunch of unitary on your input, then the resolve is on the different direction. So say you apply unitary U1 and U2 and U3 on your input state, then you actually do the calculation from right to left. So that's kind of a reverse order, and you just need to be careful. Okay. Question? No? Okay. So let's talk more about the details of the circuit model. So as we said, the circuit model composed of wires and gates, and the wires carries information around. So as we see here, these 3 wires carry 0, and you will send it into those gates. And the gates are the place where we actually do computation. And you guys are probably familiar with this, but we are still going to introduce some basic gates. So the simplest gate is this NOT gate. It's 1-bit input, 1-bit output gate, and it will just flip a bit. And so you can write it, we usually write it in this symbol, this triangle with a circle. And it will flip a bit, means if the input is 0, then the output is 1, and the input is 1, the output will be 0. So that's an example of a gate. And more generally, a gate is specified by the input-output pair in the truth table. So all the possible input and what the output it will give you. Okay. So for example, here we already have the truth table of NOT gate. We will see, because it only has 1-bit input, and we see the input bit is 0, output is 1, input is 1, output is 0. So that's all possibility. Okay. So those are gates. And finally, there are algorithm. Algorithm is just a circuit that computes some function for you. So we think the algorithm is some function, some binary function on bit string. And the input will be described in binary and put on this input side of the wire, that's the most left side. And here we use a notation that those bits we also start from top to left, sorry, top to down. So first bit, second bit, and nth bit. And those wires will go through some gate, and whatever left over is should be this f of x that your algorithm computes. Okay. So that's wire, gates, and algorithm. And as we said, we'll describe some basic gates. So we already say no. Okay, yeah. So basic gate. The first one of them is this AND gate. It's a 2-qubit gate. Sorry, 2-bit gate. So input x1 and x2. And it's one only if and only if x1 and x2 are both 1. So it is logical AND. So one of the possible input, it will give you 1, and all 3 possible input, it will give you 0. And in terms of logical notation, we'll say this is x1, and this sign is the AND here, and x2. This symbol is AND. And so there is AND, and there is OR. So OR gate is kind of a reverse of AND. It's 0 only if both x1 and x2 are 0. And so all 3 other possibility or give you 1. And in terms of logical notation, it is x1, and OR is this symbol, and x2. Okay. Then there is XOR gate. This is a little less famous than AND and OR. So XOR gate of x1 and x2 compute the parity or difference of x1 and x2. So mathematical way to write it is you add up, well, I guess the mathematical notation will write like this: x1 and this is XOR and x2. And this is basically the addition of x1 and x2 and mod 2. So other way to say this is you do binary addition of x1 and x2 and just look at the last bit. So in terms of a truth table, x1 XOR of x1 and x2 is 0 if x1 equal to x2, because 0 plus 0 equal to 0, and 1 plus 1 equal to 1, 0. And XOR of x1 and x2 equal to 1 if x1 and x2 equal to 1, 0 or 0, 1. And then there's this NOT gate. We already said NOT gate is a 1-bit gate or 3-bit, so it gives you 1 minus x, also mod 2. Okay, but here we don't. Yeah, here we don't really need mod 2, but we still write it here. And there are different logical notation that you will see throughout literature. Sometimes people write this sign, this weird symbol that means not of some variable. Or sometimes people write x bar as the negation of x. Okay, and finally there is the NAND gate. This is not AND. And just we said, NAND is not AND. So basically, this 2-bit gate. You compute the AND of x1 and x2 first, then you just apply a NOT on it. And in the logical notation, now we can also compose those logical notation. So we have x1 and x2, then apply a NOT on them. And you can see that this is composed of NOT and AND. So it doesn't seem that fundamental, but we'll later see that people care this a bit more because it is universal for classical computation. Okay. Question about those basic gates? No? Okay. And some details. First thing is we don't allow feedback loop. Okay. So we cannot have some gate and information go out, then you feedback the information to this gate. So the information always flow in one direction, as we say here. Yeah. So basically all the wires goes horizontal, and the information only flow from left to right. So there is no feedback thing. And because this can be unstable, if you want to analyze this kind of system, you need to take other course, like system and signal, and we'll analyze feedback loops. And okay, so we don't allow this in our circuit model. And another thing that can be allowed is this fan out. So we can think of this as some kind of gate that's copying information. So this fan out gate is you have a wire and you split it into two or more wire, and this wire can have input X, and the output wire will both have input X. So in terms of classical computation and circuit model, fan out is possible. You can just copy and paste whatever here down to here. But we're mostly avoiding doing this because we use classical circuit model as the basis for quantum circuit model, and this is not allowed in quantum circuit model, as we will see. And the basic idea is that there is no cloning theorem in quantum. So if this is not a classical bit here, if this is some quantum state side here, then you just cannot have fan out where you have two copies of side here. Okay. So this is allowed, but we mostly will not use this. Okay, so the circuit model. Then we switch gear again, and we talk about Boolean functions. Yeah, a lot of the portion of the class will be talking about Boolean function, and well, there are functions that have have a bit string input, and give you 1 bit of output. Okay. And I guess we already do some assumption that we assume everything is discrete in computer science, like long time ago, even since the Turing machine, right? So, but anyway, we think everything is discrete and it can be described by a 0-1 bit string. And now we restrict ourselves further into this Boolean function. That is, so by Boolean function, we mean the output is just 1 bit. The output is just 0 or 1. And we can focus on these Boolean functions because, well, you can just express other functions as a lot of Boolean functions. For example, a more general function general discrete function. It can be from some n-bit input to some n-bit output, and we can think this just as n collection of n Boolean functions, right? So you can think this as m different Boolean function that told you the first bit of output of G and the second bit of output of G, etc. Okay. So in terms of computation power, we can think if we can do any Boolean function, then we can do any function, because any function can be expressed by a bunch of Boolean functions. Although sometimes we still think about this, because thinking about the first bit, second bit, etc. is very unnatural for some problems. But you can see Boolean function is a nice starting point. It's very, very simple, and you already have lots of structure we can study. Okay, so that's Boolean function, and then there is this quite important concept of universal gate set. That is, we don't actually need to use too much gate to compute any function. So there is this nice result. We will not cover the proof. That's saying any Boolean function can be constructed or computed by a circuit that only use NOT and XOR gate, and also fan-outs. Okay. So we will not give a proof here, but that's a fact, and that means how should I say? This is nice because that means we can theoretically we can construct our computer from just very simple components. So think about we actually building computer. Obviously that's not what we actually do, but think about we want to build a computer that compute anything, then we only need to be able to build wires and 3 different kind of gates. We can only build able to build good AND gate, good XOR gate, and a good NOT gate. Then we just piece together those wires and the gate, and you can do any kind of computation by just changing the layout of how the wire hook up to the gates. So that's really nice. That means you can build up computation from just very basic components. And so NOT, AND, and XOR is a universal gate set for computing Boolean function. And actually there are even smaller gate set. You can only use AND and NOT, and even or even simpler, just using NAND gate is enough for computing any Boolean function. So that's why people like NAND gate, because it's universal. Okay. So that's that. And just as we said, that means we can specify any algorithm by describing how you put wires and you put those AND gate, NOT gate, and XOR gate on some place of your circuit. Then we'll describe your algorithm. And over 10 minutes. Okay, we can describe this. And then we come to this, back to this discrepancy between circuit and Turing machine. So, and the issue is specified in this concept of uniform circuit family. So as we said, if you draw a circuit, So some diagram, maybe this, right? And you draw some circuit, then it will have some fixed input and output size. But in particular, it has a fixed input size. Okay. And but we want to solve a problem, then we want to probably solve it for different input size. Actually, we want to solve the input size. We usually want to study asymptotic, so we want the input size to go to infinite. And so want the input size to go asymptotic, go infinite, but the circuit has a fixed input size. So if we want to actually describe an algorithm, then what we describe is not one in circuit. We'll describe an algorithm as a circuit family. And that's just the infinite size set of all the circuit for different input size. Okay. So that works. You just have this family that's infinite size set, and they will have circuit for 1 bit input, circuit for 2 bit input, etc., all the way to infinite. So this way you can cover infinite input size with all different circuits. But then this gives a problem. That is, if you just say, oh, my algorithm are those circuits, then you can cheat by not actually having those circuits to compute. So because you can say, for the first input, I will just output whatever truth table of the from the input. You can cheat. You can hard code the answer onto the description of those circuit. For example, this actually give you the power to solve 14 problem, because your circuit can just hard code your 14 number into it, and presumably it's actually possible to have a circuit family that give you the 14 numbers. And that shouldn't be possible. So actually, if we want to go very fundamental, how we solve this is we go back to Turing machine once again. And so we want this circuit family to be what we call uniform. And that means we want the circuit family to be something that can be computed by a Turing machine. Okay. And yeah. And that means you will have a Turing machine that take the size of the input n here. So this Turing machine will take n as input and tells you Cn. So it will tell you where to put your circuit, where to put your gate, and where to put your fan out, etc. So if your circuit family is computable by a Turing machine, then we call it uniform. And then the uniform circuit family cannot really cheat. So for example, because the circuit is computed by a Turing machine, then a uniform circuit family cannot solve 14 problem, because no Turing machine can solve 14 problem, and they give you a truth table of 14 numbers. Yeah. So this is how theoretical computer scientists give a very rigorous definition of algorithm as a circuit family. It needs to be a uniform circuit family, and we go back to Turing machine. And you can see that Turing machine are very why Turing machine has this very fundamental position in computer science, because it's very robust and don't have weird problem like non-uniform circuit family. And okay, so that's some theoretical concern about circuit family. But back to more practical terms, most algorithms construct uniform. So we will not check whether our circuits are uniform or not. We will not worry about the uniformity of our circuit too much throughout the course, but this is just something nice that you can keep in your mind. Okay. And okay, we will save this for next class. Well, a little early, so let's have a bit longer break. Next class we'll go over this big O notation and more about computational complexity. Okay, let's stop for now and go back at 4:30. Okay. Any question? Otherwise, let's take a break.不一样吗？
我一样是，我想问就是，他讲说就是可能，比如说我从这边画到这边，然后 n 跟 n 分别代表它的input的数目这样子。
input 跟 output size。
对，然后所以说我是不是可以讲说，就是可能这个 n 跟 n 是分别是可能我设 f0 of x 跟 f of x 的自由度。
对啊，这里 f0 跟 f 是什么东西？
就假设我左边这个是 f0 of x， 然后右边是 f of x。
那 x 是什么？你说 n 跟 x 是什么东西？
就是可能它下面有这个东西，就是这个，就原本是一个 f0 of x， 然后里面有 n 个 x 这样子，就1到 n。
n bit。
对，然后会变 f of x， 然后变0到 n， 这边 n 加1个，然后可能等于 n 个这样子。就是上面这个是 n 个到 n 个。
我觉得听起来对不太起来，它下面写这个什么？我看一下，我不太记得。n bit， 它是说什么东西啊？这个是，不太记得。any function。boolean function， 它是想要证明。Use gate。那真的是不同的事情。他是说，他这里是在证 universality 的样子。我看一下 ，when I prove the simplified case， boolean function。等于1。它这里已经变成boolean function了吧？
我想说，这好像是跟就是讲，就刚刚。
没有，他在讲的是不同的事情，他是在证 universality 的事情。
所以说下面讲那个 x。
他已经在boolean function，他现在是 n 变成 n 加1的事情。
所以说 n 变 n 加1的行为跟 n 变成 n 这个行为是不一样的。
跟这里 n 从 n 变成1是不一样的事情。对，它 n 变成1的事情就这里已经结束了。他这里是在说，我只要做什么？他是用什么 not 跟 and 吧？他是用 not and 跟 or， 然後说我可以算 n bit 的boolean function， 然后我就可以算任意的 n 加1 bit 的boolean function。
因为我刚刚想问说，就是依照这个逻辑，那我可能 n 个音符变成 n 个音符过程，那我一定是有一个规则嘛，就是它的增减是有规则的。
n 变成没有这个 怎么说 n 个 bit， 这个什么规则对应方？我现在 G 是个01到 n 到1到 n 的容积。
其实可以猜 n 个小的。
对啊，这个马上就可以看出来是 n 个小的函数嘛，因为比如说 G over x， x 是某个 n bit 的东西，就等于它会是某个 G1、G2等等。例如说我 fix 某个 x 然后这样写嘛，然后它会给你一个什么01、01、01、会给你一个 n 个 bit 的 output， 这种感觉，对啊，是 n 个 bit input 到 n 个 bit output。然后现在这个转换就只是说第一个 bit 我就叫这个叫做什么的 G1 over x 嘛，然后这里有 G2 over x， 然后最后有个 Gn over x， 对吧？对吧？然后这个是不变的，因为它只有一个 bit， 然后这个是不变的，它只有一个 bit， 然后这个是不变，它只有一个 bit， 就只有讲这种事情而已。所以这个 G1 到 Gn 的这些东西，这 n 个不变方程，你会发现它就会完全描述你的这个 G 的方程，对，所以就只要讲这件事情而已。
我在写作业的时候，都在记得，就是那个 pure state 到底是，
对，
到底怎么？
科学题目在问什么？没关系，你问问看哈。
就是那个 purification， 为什么印出来的那个 pure state 那个东西是为什么？
你写一下好了。这个是 streaming decomposition。
对啊，那个 pure state 是然后 A 如果你要把它做 pure 然后好像会，对啊，好像是。
这个 purify 有很多方法。
要对的话也是purify，然后变成3。
有这一题吗？那确认的，没关系，
只是想到说，为什么它那个是 pure state？
purify 本来就是要变成 pure state 啊。
可是它的形式。
你是说这样子不是 pure state 吗？这样是 pure state 啊。
它是变成根号体啊。
对啊。
对，为什么这个是 pure state？就是看起来好像很多东西，然后加起来好像是隐身。
entangle 跟 pure 是两件事情，不要搞混。就 entangle 对应到是 product state。
差不多像隐身。
这个不是 entangle 啊。这个是 superposition of pure state 还是 pure state？product state 对应到 pure state， 然后 mix， 然后对应到 entangle state， 然后 pure state 对应到是 mix state 啊，不要搞混了。所以你可以同时 pure 用 entangle 的是可以的。
那 pure state 应该是
没有，就是一个 vector 就是 pure state 嘛，你想。这个先讲这个好，这也比较 confusing。这个对应的是有两个 register 的是东西嘛，这里有 A 跟 B， 然后 product 是说你可以写成塞 A 填成塞 B 这样子。对，这个叫 product state， 然后 entangle 就是不是这个的，对。然后 pure state 的话就是，要用 density matrix 来想嘛，它可以写成塞。如果你的 density matrix 是个塞 A 的东西的话，它是 pure， 然后如果不是的话就。
是只能用 density， 只能拿来描述 density matrix。如果是要描述这个可能是这个 vector 这个
可以用 vector 描述的就已经是 pure state， 不能用 vector 描述的才叫 mixed state。你们这个是个 vector 吗？这是一堆 vector 加起来，它还是一个 vector。
所以 vector 一定就是 pure 的。
对 ，vector 的就是 pure 的。
哦。
因为你想说，因为这个人两个 qubit 看起来有点混乱嘛，但你想一个 qubit 这个0，然后根号2倍的0加上根号2倍的1，这个还是 pure state 嘛？那这个也一样，你有一大堆 vector， 这些都是 pure state， 然后你把它弄个什么 weight 加起来，那它还是个 pure state。
到后面有点混乱，它那个。
对，但是这个 trace 不 trace 的事情就有点混乱。
像 pure state 又等价。
pure 又 entangle， 然后你把它 trace 之后的东西会变成 mixed state， 然后 pure 又 product 的东西 trace 之后还是 pure state。这是我在那个 streaming composition 那里在搞的。我现在变成有两个东西嘛，那我们说我们已经假设它们合起来的东西是 pure 的，然后现在在看的是这个合起来的东西是 pure 之后。然后我就分说，它有对，然后它有可能是没有 mix 要 pure 的嘛 ，pure 就已经 pure 了，对，它合起来就已经是 pure 了，然后我们可以把它写成 stream decomposition， 然后那它有可能是 product state 或者 entangle state， 然后如果是 product state 的话，所以有两个东西嘛，一个在 AB， 然后又有一个 row A 这样子。然后如果它是 product state 的话，那你去把 B 这里 trace 掉，然后去看这个 row A 的时候，那它这个 row A 还是 pure 的，因为它就长这个样子嘛，那你 trace 掉这个塞 B， 基本上这边就还是塞 A。对，就浪的 I 就只有一个1这样子。然后，但是如果它是 entangle state 的话，那你这里就有很多不同的浪的 I。那你 trace 掉完之后，你这里的 row A 就会变 mixed state。
如果这有多个就是。
对
，I 大于1的这种。
对对。
后面不是有个整理说到 pure state？
对啊，基本上是在讲这个嘛。
然后不是有讲到一个，如果它让它是1，这个就会是 pure state。如果它变 pure rotation 就变。
对吧？就是刚才讲那个嘛。如果让它是1000的时候，那就是看两个东西的时候，这个是 product state， 然后 reduce 下来这个会是 pure。对。
那还有另外一个，如果是两个系统的这个确实都会这个变。
这个你就去运算它的 trace 了。
是谁？
我想想看，应该也可以分两边的 trace 做吧。你也可以先算 trace A 再算 trace B， 但直接算比较简单啊，就是你就想成是 matrix 的话，就是想写成比如440的 matrix， 然后把它全部加起来。
因为有一题好像证明 product state if and only if row A 是 pure state。OK。但那个只有一个。我想说 row A 写成这个，然后
也不用 I A I B 吧，它就一个东西，你就让它 I， 然后 I 就好了。因为没有你，因为哦对啊，就写这样就可以了。对啊，没有，不是这样的。没有。
是这个吗？它不是会变两个东西？
你现在没有两个的structure，为什么？应该没有吧？我看一下问题。我们的问题有这个怪怪的 structure 吗？我找一下，不要小心跌到解答。我会跟你讲。你已经教了？靠右我都没有。 等一下，我还是拉出来。
它是 pure state 可以 decompose。
哦，你已经教了，那我，
pure state 可以变成这样。
没有，这个是我们考虑说这个 pure state 在2个系统上，你才会把它变成这样的。那如果我就合起来看，我把它当做一个大的，就是 A 乘 B dimension 的东西，那我就不需要这么复杂嘛。我可以就直接说，
就是因为它有要计算 low A 这个东西，所以还是要算。
到底是出了什么题目？为什么觉得听起来
怕它
很诡异
？low A 是 pure state。
我先试着登入。
还是要先上。
应该要先上课，但是我现在我看一下，我稍微看一下。你说的是哪一题 ？Product state if and only if。哦 ，OK，sure。
在 A B C 上。
哦 ，OK。对，你要拆成这样子，然后怎样？也就是。
就会是，因为它是 autonomous 嘛，所以它只会留下 I 项。
对。
I A I。然后同时 I B I。
你这个是，也对吧？你这是全部都是 low A B 的，对。
然后我想说对它，因为它是 pure state，然后想要做这件事，然后这个就变44。
为什么会变44吧？哦。
对，2个，然后这个就消掉，然后就变44，然后再取确实，然后再取这个，就最后是对的，对。
等一下我再讲 ，OK。OK。Hello. Sorry, wrong screen here. Okay. So any question from the circuit family formulation of algorithms, or in general the circuit model? So a circuit model will be mostly how we think about algorithms, and obviously also pseudocodes. Hopefully everyone are. We will not give a more formal description of pseudocode, so hopefully people understand pseudocode. But here we have an introduction of circuit model, and this will also be how we describe quantum computation. We will replace those gates with quantum gate, and we'll assume those wires going to carry quantum information. Okay, so that's circuit model, and some complexity theory around them, the universal gate set, and the uniform circuit family. And then we go to this idea of big O notation. This is probably the most computational part of the chapter, and as a spoiler, this will be in your meter, so you better be a little more careful here. So big O notation, the motivation is as we keep saying, we want to study the asymptotics of our algorithms. So we want to study how fast the function grows, say the input size. And there are 5 different notations here. So there's big O, small o, big omega, small omega, and this is theta. So there are 5 different expressions. We'll say some function of n is big O of another function of g of n, or small of g of n, and those two basically means g is the upper bound of f, and we'll see their difference later. And those two means that g is the lower bound of f. So big omega and small omega of g means g is smaller than f, and that means g is the lower bound of f. And lastly, this theta means g and f grows about the same rate. Okay, and let's give more technical definition. So this big O, we probably see this most, and it means we say f of n is g of n. That means so we give this very calculus definition. This means there exists some constant c and n naught, such that for n bigger than n naught, f of n is smaller or equal to c times g of n. So you see, this is really asymptotic. We are trying to see how g and f grows as n go to infinity. So there is always one scaling parameter in those big O notation, and here we choose the number as n, but it can be x or y or something else, or big N, it can be different. And sometimes things are very confusing because there are two scaling notate. There are more than one scaling symbols. Say your algorithm, there is input size x, and sometimes there is also error epsilon. So you think about how your complexity grow with x and epsilon, and that is a bit tricky. But for now, we assume everything is very nice. There is one scaling parameter, and we call it n here, and sometimes we call it x. Yeah. And here we see this big O, as we say, f of n is big O of g of n, means f of n is less than g of n. And this is describing asymptotic because we only care about this thing happening when n is very large, n is bigger than some fixed number n naught. So let's draw a picture. So this scaling axis is n. So maybe your f of n look like this. Sorry, that's not the function. So maybe your f of n look like this thing, and your g of n look like. Let's change the color. How about this? Your g of n look like this thing. Then you see that f is bigger than g on some low part, but for some n naught here, right? So once your n is going through some threshold, your g is always bigger than f with some constant multiplier. Okay. So that's kind of the mental picture. When your n is bigger than something, then your g is always bigger than f. Okay. Question? Okay. And so that's big O, and there is also small O. And the difference is that instead of exists one c where f of n is less equal to g, now we want to have for all c, for all possible constant, f of n is less than c times g of n. And so the difference between those two is this big O is kind of f is greater or is less than equal to g, and the small o is like there is no equal. We think f is just less than g. Okay, I should finish this saying this. So for OC, there is n naught such that for n bigger than n naught, f of n less than c times g of n. So this c can be 1. So for c equal to 1, 2, 3, 100, 1000, you need to find the n such that this is true. So for example, here maybe f of n equal to n and g of n also equal to n. Then you can have a c here, and that's true. But for this thing, then the g needs to be actually growing faster than f. So maybe f needs to be n, and g equal to n squared. And then you see this n naught will depend on c. So say you have some c here, then you want c n squared bigger than n, then you will want n naught also equal to c. Right? So did I have this correct? I think it's 1 over c. Wait, actually, sorry. Anyway, this not will depend on c. Okay. I think if it's c, then yeah, it should be 1 over c. Sorry. Something like that. But you see that the g need to actually grow faster than f for this small O to be satisfied. But most of the time, this big O is what do we use? Small O you usually use for something. I think small O usually uses for small of 1. So you want something that's smaller than constant. Okay. And okay, so that's big O and the small O. Then big omega and small omega basically just reverse this. So big omega is kind of like f is greater or equal to g. And in terms of the detail, you say that f of n is big omega of g of n if there exists also a constant c and another constant n naught, such that for all n bigger than n naught, f of n is greater or equal to c times g of n. So basically just swap between these two sides. So now f is like bigger one, so f is like this dark green line and g is like this green line. So I guess this one is like small, and I should draw something that look like that's annoying. Let's draw like here, like the omega thing. So maybe your f look like this thing, and they are sympathetic to something. Not like this. Maybe your f is like this, then go to a straight line. Then your g is, oh, I can just draw here. No, that's annoying. Yeah, and your g is maybe something else, and also sympathetic to is something else, and sympathetic to something else. It's also a straight line, but it has different slope. Then this will be this will be f is small of g, and yeah. Okay. And then there is okay, let's finish describing this. So that's big omega. F being big omega of G means that F is bigger than G for all big N. And similarly, there is F of N being small omega of G of N. And that means for all C, there exists an N naught that can be dependent on C, such that F of N is actually bigger than C times G of N. And something we forgot to say. And here, for simplicity, we assume every function and the constant, etc., are positive. Yeah, so we should probably cut off this and this. And if the things are not positive, then I think you should add absolute value. And usually, for complexity, we only think about positive F and G, because F and G are going to be cost to your algorithm, like the time cost or space cost, and obviously the costs are positive. But anyway, we have big omega and small omega, and finally there is theta. So theta basically means, as we said, this is like F equal to G. F equal to G. So F of N equal to theta of N if there exists two constants C1, C2, and also another cutoff of N naught, such that for N bigger than N naught, F of N is sandwiched between C1 of G of N and C2 of G of N. So this means that when N is very big, then F and G are basically same number, just different by some constant that might be oscillating, but in some region. So this is kind of a description of F equal to theta of N. So once N is bigger than this N naught, F of N grows like G of N both linearly. And you can also see that, I think that's also your homework, where F of N, F is big theta of G, if only if it's both F being big O of G and F being big omega of G. And intuitively, that's just if F is less than equal to G and is both bigger than equal to G, and that's just F equal to G. Okay. So question about these quite technical definitions, but I think the bottom line is, yeah, you can you can remember these these 5 ideas of the relationships. So big O is like F less than equal to G. Big O is like less than equal to, and small is like less, and big omega is like greater or equal, and small omega, I didn't say, small omega is like greater, and big theta is like equal. And everything is asymptotic, so we only care about there is some cutoff N naught, and all those greater or equal small 2, you can multiply by some constant. And now there is quite important cheat sheet here. This thing, hopefully you learn in your calculus. So we have those about 4 scaling groups that we care most. when x go to infinity. So the first one is constant, and it's obviously less than log of x, or sometimes we'll do polylog, so some polynomial of log. And log of x is less than any polynomial of x. And then any polynomial of x is less than exponential of x. So this is a quick cheat sheet. And more example of some scaling relationship is that, so n squared is big O of n cubed. This means n squared is scaling, n squared is scaling slower than n cubed. And generally, if you have any polynomial, you have n to the a equal to order n to the b if a is less than or equal to b. Okay. This is quite simple calculus, or just algebra, you can check. And one example of this is this n squared is order n cubed. And as we say, example of small is people often use is small of 1, means something that's even smaller than constant. So something even smaller than constant can be like 1 over n, or 1 over poly n. So as n goes to infinity, this thing actually goes to 0, right? So that's why it's less than just a constant. And then we have the reverse of first relationship, where we want to study where something is scaling as n to the cube, and we can give a lower bound of n squared. Obviously, n cubed is scaling slower than n squared, just as we said. And then we have this example where where we see how this big O notation is useful because it saves lots of detail in our scaling function. So for example, we have a function that's 2n squared plus n. Then we want to say what's the big theta of this thing, and it will just be n squared. Because as n goes to infinity, this n squared is much bigger than this n. So this n squared will just dominate this n, and this n doesn't affect the scaling. And also this 2 doesn't matter because in this notation we have the C1 and C2 that will account for the constant. So when we have the polynomial of whole bunch of polynomial of n, then in terms of this big O notation, it's just big theta of the highest order term. Okay, that's really nice. And finally, as we said, any polynomial when n goes to infinity grow less than the exponential function 2 to the n, or here 2 to the x. So even for n to the 1000, it's big O of 2 to the n, means it grows slower than 2 to the n. Although this is quite purely theoretical, because in practice, if you see this n to the 1000 function, then it also grows very fast, and it might be even slower than your exponential function. But in pure theoretical term, then n to the 1000 is slower than 2 to the n. Okay, question about big O notation. So hopefully you learn this in calculus or in other class. This is an important concept that you need to know and do this kind of calculation This calculation are all very fast if you get used to it. And basically you need this cheat sheet of those two class we care most about: the constant, polylog, poly, and exponential. And remember, when you have polynomial, then then you only care about the highest order term. I think that's the most important thing about the big O notation. Also, there's something we won't care too much about, but I think people should be careful. That is, for this big O notation, people often abuse this big O. Okay, so by that I mean people will use big O to represent things that are actually big theta. Right? So for example, this thing, 2n squared plus n equal to big theta of n squared. It means we think this scale as n squared. And but sometimes people write this as big O n squared. Well, that's not wrong, because big theta is a stronger condition than big O. And it's just sometimes it's when you should write big theta, you write big O, then it's a bit misleading, or there is a bit mismatch between what you mean and what you write down. So you write this, but yeah, when you write this is it's a good habit to remember that big O is not big theta. Big O means G is bigger or equal to F. I think in some of the lecture notes we also made mistake, but this is a good habit to keep track of your own writing, to not mismatch big O and big theta. Okay, any question about big O notation? Okay, if not, we have 20 minutes. Okay, so we can talk a bit more about computational complexity. So computational complexity is, well, it's a big part of computer science, and this is a part that I personally are really interested in. And I believe this is also not only fundamental but also very close to practical part of the computer science. And it studies how much resource needed to solve a computational problem. And for the theoretical so if you want to be very practical, then it's this part: how much resource we need to solve a computational problem. And we are theoretical, so we care about how those two things scale asymptotically. That means we want to study what happens when your input scale to infinite, and how does your resource scale. And this is a very different mindset compared to what we just talked about this class, the halting problem and the Turing machine. There we didn't really care about how much resource we use. So for the halting problem, people only care about whether a problem can be computed or not, so being decidable or not. But this resource perspective is obviously much more modern. So after people actually build computers, we realize even for solvable problems, sometimes it takes very long time for your computer to run. So say we want to see when you have some computational problem, how much resource actually need to be used to solve your problem, and sympathetically. So there are three keywords here. There are resource, and there is what is a computational problem, and what do we mean by sympathetically. So asymptotic we kind of already introduced in this big O notation. So sympathetic means there is a scaling parameter, usually the input size of your problem, and we think that thing go to infinite, and we want to see how other things scales in terms of these big O notations. And now we want to describe what is a computational problem. Okay. So a computational problem, very very theoretical perspective, is we focus on decision problems. So decision problems are problems that output a yes/no answer. And we also kind of see this in just last class. That is the decision problem correspond to computing a Boolean function. Okay, and so that's decision problem. Decision problem computes a Boolean function. And somehow we give this even more formal definition. Okay. Basically, this once again, a Boolean function is something that has a fixed input size. And when we describe a problem, we want to describe it for all input size. So we have this more concept, this extra concept of formal language. So this formal language is not to confuse with natural languages like English or Chinese. So language for complexity theorists is a subset of strings. Okay. So subset of string, and a string we write in this weird notation 0, 1 to a star. So 0, 1 to a star means a string of arbitrary length. Okay. So 0, 1 to arbitrary length. And language is a subset of all strings. So for example, we can have a language that's all the strings that only contains zeros. So 0, 0, 0, 0, 0, 0, or 0, 0, 0, and etc. And so that's a language of infinite size. And we can also have even simpler language. So a language that they only have two elements, 0 and 1. Okay. And so this is very simple set theory. You have some set, and language is a subset. And as we said, we define this formal language because we want to describe Boolean function. So basically, there is a very easy connection between Boolean function and formal language. That is, or a decision problem and a formal language. That is, given language L, we can define this decision problem that works on any input size. That is, you give X, you give your input, that's some bit string of arbitrary length. Then you want to decide whether your input is in your language, like this, or not in your language. Okay. And so your decision is yes So you should give a yes answer if input is your language, and no answer if input is not in a language. So you can see that this formal language is actually just the idea of you just put the input of all sides together, and you label them as output being 0 or 1. So output is 1, then you put them into your this subset of language, and the complement of this language is all the input that give output 0. Okay, so maybe easier to see this example. So your decision problem related to this language of all 0 strings, and you ask, is this input of 0, 0 in your language L1? And the answer is yes, so you should say yes. And is your input of 0, 1 in this language L1? Then the answer should be no, because there is a 1, it's not a all 0 string. Okay. So this is just another way to describe Boolean function, but you put all the input sides together. Basically, this is basically a truth table for your Boolean functions. And well, there are a lot of things you can do in Boolean function, just like we said. So, for example, the Boolean function, we can do primality testing. So basically, you can ask, is your input a prime number? And so we can define the corresponding language that is all the prime number. So it will be 2, 3, 4, 5, 2, 3, 5, 7, etc. And in terms of Boolean bit string, then it's 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, etc. So you can see there is although we didn't quite explicitly say, but you can see that there is a one-to-one correspondence between a decision problem and a formal language, or more like formal language is how we formally describe decision problems. Okay. Or family of Boolean functions can be has a one-to-one correspondence to a formal language. Okay. And we have 10 minutes. We can probably talk a little more. Okay. And so as we say, computational complexity, we want to see how much resources are needed to solve computational problem. And we describe computational problem as formal language. Well, this is a bit restriction on computational problem, but for now we focus on decision problems. And so that's computational problem, but then now we talk about resource. And there can be all kind of resource. So for example, we think about our training deep learning model, or like mining Bitcoins. There are resources like how many GPU you need to use, how much energy, and how long it takes. So those three things. Somehow we only care about two of them in computational theory. So it's quite hard to model how much energy, how much power, how much energy you use in a computation. But it's pretty easy to model the time and the space you used in your computation. So time used in your computation, this is well, quite concrete example. So some computation you do in your laptop, or simulation, or etc. It's a quite concrete concept. It's how much time spent when you do computation. And in terms of the model, we have introduced in this chapter, the time use can be modeled as the number of gates you put in your circuit, or number of steps in the Turing machine. Number of steps that the Turing machine has run before it halts. And the other resource, so time is usually the most important resource we think about. And but also we would like to think about the space. And this is also something very important. Sometimes it's very important in practice. So space is the well, in terms of actual computer, this is basically the number of runs you need to have in your computer to run your algorithm. And in terms of the models we introduced in this chapter, the space is how many wires, so the number of lines in your circuit model. And in terms of Turing machine, is the number of tape, although we say the tape is infinitely long. But if we really want to count about the space, then the number of tape blocks that actually get used in a Turing machine is the space of your algorithm. Yeah. And obviously those two numbers in two different models are going to be different, but we think that when we only take about sympathetic, so when the problem size scale to infinite, then they are quite related. They are usually related by polynomial. So those we can think in different model back and forth. Okay. So time and space are the resource we'll focus on in discussing computational complexity. And finally, we can describe this concept of complexity classes. And the motivation of complexity class is we want to classify how hard the problem actually is. Okay. And well, some of the reason is actually that some of the problem that we introduce complexity class is because it's hard to compute the complexity for some problems, so we just give a rough grouping of problems into complexity classes. Anyway, the intuition of complexity class is a set of languages that are about as hard as each other. And so remember, the languages are basically computational problems. So we want to group a whole bunch of computational problems that we think are about as hard as each other into a complexity class. So for example, this very famous complexity class P, it stands for polynomial time. And a set of all languages that can be solved in time that's polynomial. So time big O n of k for some constant k. And where this n here is the size of input, that's the length of length of the input x. Okay. And P is, well, P are what we think of as easy in complexity theory, because, well, in practice they are also quite doable. And this easy will also be interchangeable. This word easy is interchangeable with efficient and solvable. Okay. And this is actually something that works out very nice. So in practice, usually when a problem is a P, we can actually have a pretty practical algorithm to solve it. Although there are edge cases that this is not practical. So as a disclaimer, so say only want n to the k to be a constant, and let's say you have something that's n to the 10,000, some algorithm that's in n to the 10,000. Oh, sorry. If some problem that need to be solved with time n to the 10,000, then this is not actually a practical number, but it's still in P. But this don't usually happen. So we think that is P being efficiently solvable is a pretty good approximation to reality. Okay, so there's that. And so just something that I state about. So remember, P is a set of problems, okay? The set of language or problems, and so problems and algorithms are different things. Algorithms are things that try to solve your problems. So it's actually misuse of a notation to say your algorithm is in P. Okay? So you should say your algorithm is polynomial time. But the algorithm is not in P because P is a set of problems, not algorithms. Yeah, that's something people do, and I also sometimes do this, but it's better to be a bit more careful and not say your algorithm is in P. You just say your problem is in P and your algorithm runs in polynomial time. And finally, so P is really nice, and another nice thing about this is P is equivalent in multiple computational models. And for example, this will justify our slash line here. So if you have used polynomial number of gates in your circuit model, then you will also use polynomial number of steps in your Turing machine. So P here is equal to P there, and so that's a very good definition. It kind of doesn't care about what computational model you use. So we just gave two examples here, but people have tried different reasonable models, and they all convert to each other with polynomial overhead, and so P is robust against all those different definitions of reasonable models. And I think we are just on time. So we'll talk about more complexity class next time. And any question? If not, then let's stop today.